The Big Bang Theory states it's a bit of a misnomer because we don't think there was a bang. We don't think there was a big noise or a big explosion. We just think there was a rapid expansion. So my area of expertise is in gravitational wave astronomy, which is essentially the ripples in space-time that come from two accelerating very massive objects. So for example, if you have two black holes, which are very dense and very massive, and they're orbiting around each other, then they cause these ripples in the fabric of space-time itself. Einstein's theory of general relativity tells us that gravity is not a force that pulls. It is the fact that if you have mass in the universe, it bends space-time in such a way that the path of objects are changed. One of the rules of the universe seems to be that you cannot go faster than the speed of light. Remember in Interstellar when the crew, they go down to that planet that was very close to the black hole and one crew member stays behind in the spaceship, and for them just like a couple of hours pass, and then for him like a couple of decades passed, essentially. That could happen, like time would be slower for someone who is very close to a huge gravitational source like that than it would be for someone who is much farther away. So that is a realistic interpretation of that. But the bit where they fall into the black hole and he's going back and putting like little bits of things in time, that wouldn't be possible.
In astronomy, you're chaotic. You are doing a lot of things in astronomy, like events are going on, then a lot of research projects you have done, a lot of theses you have written, like research papers you have written, I saw. Which area of astronomy interests you the most?
Oh, geez. Well, so my area of expertise is in gravitational wave astronomy, which is essentially the ripples in space-time that come from two accelerating very massive objects. So for example, if you have two black holes, which are very dense and very massive, and they're orbiting around each other, then they cause these ripples in the fabric of space-time itself. And so for my PhD work, I studied what sort of models we'd need to use to be able to detect these ripples in space-time using modern detectors such as the LIGO Observatory, which made its first detection in 2015, and that was after I graduated, so it was kind of interesting for that to happen at that point, yeah.
So before we start all this,
yeah.
Let's first of all talk about what is black hole,
Sure.
and what is the fabric, what term you used?
The fabric of space-time.
Fabric of space.
Yeah.
What is that?
Okay, well, so I'll start with black holes.
Okay.
So, because that's a little bit easier. So black holes are objects that are so dense that even light cannot escape from their surface. So you think of like the Earth or something like that, and in order to escape the Earth, you have to be traveling at a certain speed, right? And rocket ships go at that speed so that we can actually escape the Earth's gravity. The more massive an object is, the faster you have to go to escape the gravity of that object. But if you have a black hole, which is this very, very, very massive object, you need to be going faster than the speed of light to escape it. And nothing can go faster than the speed of light. And so that means that even light cannot escape from this object. So usually black holes are due to the collapse of the core of a very massive star after it goes supernova at the end of its life. And so it becomes this just infinitely dense, very compact object, which has this point around it called the event horizon, which is that point at which light cannot escape from the black hole. So the black hole itself, all the mass is contained in like one little point, but you have this region around it that is completely black because no light can escape from it. So we've actually detected black holes, but we can't see them directly, obviously, because light cannot escape from them.
So we've used telescopes to detect.
Indirectly. So the most recent image of a black hole is we've taken an image of the black hole at the center of our galaxy, which is called Sagittarius A star. And what you see in this image, you might have seen it in press releases or whatever. It was in the news for a while. It basically just looks like an orange donut with like a black circle in the middle.
Yeah.
And so that is a black hole's event horizon is that black circle in the middle. It's the point at which light cannot escape. And then that orange glow around it is matter, which is currently circling around the black hole. So it's spiraling in towards the black hole. It may eventually fall into the black hole, but because it's moving around the black hole very quickly, it gives off a lot of light. And so that's what we're actually detecting. We're not detecting the black hole itself. We've also indirectly detected black holes through X-ray emissions from that same disk of material where all the stuff is getting sped up and you see it glowing very, very brightly. And we've also just seen the effects of the gravity of the black hole. So at the center of our galaxy again, there's this huge supermassive black hole, and we've been able to detect essentially stars orbiting around this empty space. And this was something that won the Nobel Prize a few years ago with Andrea Gheze's team. And it's essentially, you're just seeing like nothingness, like a point in space, and then you have all these stars that are orbiting around that point in space. And so if something has a huge amount of gravity, enough that stars will orbit around it, but does not emit any light, then one has to assume it's a black hole. And we estimate that this black hole is about 4 million times the mass of our sun. So that's a very, very big one.
There is this Indian scripture.
Okay.
And I'll translate a line from that. It was recently made into a song as well in India. जब कहीं पे कुछ भी नहीं था, or if I'm getting it wrong, जब कहीं पे कुछ नहीं भी नहीं था, it's like that, it goes like that. And the meaning of it is when even nothingness was not there. And you just talked about the stars, and you just talked about this thing that even there is nothing beyond the universe, and there is no end to the universe.
Okay.
We talked about it. What is the vastness of universe if we talk about it? Like how...
I don't want to finish the other thought. Because you asked me about the fabric of space-time as well.
Yeah, that's what I'm talking about.
Okay.
Just curious.
Okay.
When we talk about fabric of space-time, most people assume there is some end.
Right.
Right? If there is no end, what is beyond? And what is this fabric? I have seen this one video in which there is this bed sheet that they have put it like this, and there is sun in the middle, and something is rotating.
Right.
And how do we explain this theory of space fabric?
So it's not an actual fabric. It's not actual material. It's vacuum. But the analogy you're talking about with the two-dimensional sheet, that is sort of a visual aid we use to help explain how gravity works according to the theory of general relativity. So Einstein's theory of general relativity tells us that gravity is not a force that pulls. It is the fact that if you have mass in the universe, it bends space-time. This fabric of space-time. It bends space-time in such a way that the path of objects are changed. So it's not that there is, something tugging on something for there to be matter moving. It's that you have mass and it's actually warping our reality a little bit. So what that translates to in a more concrete kind of way is that lengths can change, and time can also change because of that. So that this idea of the fabric of space-time is that time and space can be warped and distorted, and that measurements of both time and space are not fixed throughout the universe. So when I said earlier that the movement of objects causes ripples in the fabric of space-time, what that basically translates to is that moving outwards from these two black holes, for example, there's a slight lengthening of space and shortening in space, and lengthening in space and shortening of space. And it's so slight that it's very hard to detect, but it is actually measurable. And the first gravitational wave detection, the first ripple in space-time from two black holes that were spiraling around each other and then gradually crashed into each other, that was that was measured by these very slight changes in length through the detector as the waves pass through.
So they're like ripples and waves of what?
Of length, if you can, of length and time, of distance and time. So it's not of anything, it's of what everything is embedded in, essentially. So it's not a physical thing that we can touch and measure and pull apart. It's reality itself. It's like what we're all sitting in. So we measure with a ruler a length, and then if we were to see that same ruler over there and there's a huge gravitational field, that ruler would be of a different length.
Interesting.
If we're measuring like 1 second over here, if we went right next to a black hole and we tried to measure a second from over here, it would seem a lot longer. Like if we put a clock and it was going tick, 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 right? If we put a clock next to a black hole and we're observing it from over there, the amount of time it would take to go from one tick to the next would be longer than it would be over here, even though it's an identical clock. So when we talk about the fabric of space-time, it's basically just this idea that space and time are malleable. They're not fixed. Like distances are not always the same. Timing is not always the same. And that's one of the big things that came out of general relativity, was this idea that lengths can change, timing can change, and gravity itself is warping space around it. If that makes sense.
Length and time can change.
Yes.
There is this theory that floats around. We say time is a dimension. Time is a new dimension. How do you define it through astronomy?
Jeez. Well, so it's not new. We've always measured time as a dimension of sorts. It was really when Einstein came up with general relativity that it was a dimension that was tied in with the three dimensions of space. So you have length, width, height, and then time. And time is essentially just how things change in one direction, right? So we think of this like arrow of time, like everything is always moving in one direction, we can't move back, and that's the only difference between time and space. But it's a huge difference, right? Because in space I can say, okay, I'm going to go over here, and then I'm going to go back over here, and then I'm going to go back over here again. You can't do that with time. We're stuck in time. We can only go forward, right? It's like we're on a roller coaster that won't stop.
Talking about time traveling, how is that possible then, if we talk about this thing, that we can just go in future but not in the past? Are we saying about that?
Well, so like you as a person, have you ever gone into your past?
In thoughts, yes.
In your thoughts, sure. But physically?
No,
right?
Impossible.
It's impossible. So time is something that is measurable, it is going forward, but you can't travel back in it. And there are various laws of physics that, you could warp around some things, use wormholes or something, and maybe travel back to a previous time. But in physics in general, we assume that there is one direction to time. Like it's just an arrow pointed this way, whereas for, length, width, height, it's an arrow that points in all the directions. Like you can go backwards and forwards.
So can I say that Interstellar movie defines it almost...
Well, actually, that's a good example of time not being a constant, though, right? Because remember in Interstellar when the crew, they go down to that planet that was very close to the black hole, and one crew member stays behind in the spaceship. And for them, just like a couple of hours pass, and then for him, like a couple of decades pass, essentially. So that could happen, like time would be slower for someone who is very close to a huge gravitational source like that than it would be for someone who is much farther away. So that is a realistic interpretation of that. And there would also be huge tides like there were on that moon or that planet and all that stuff. That was pretty accurate. But the bit where they fall into the black hole and he's going back and putting like little bits of things in time, that wouldn't be possible, because physics tells us that in order to, even like in the most wild conceptual things where you make up wormholes and things like that, it's impossible to go back to a time before your time machine existed, right? So you could have established your time machine and then you could go back to that point, but you can't go back into a past prior to that time machine existing. So, by time machine, I just mean anything that is circumventing the regular path of time. So that movie was great up until that point when then fell into a black hole and whatever. But like we are all time travelers. Like I am traveling through time at a rate of 1 second per second. If I was to go very close to the speed of light, time would pass 1 second for me, 1 second per second for me, and 1 second per second for you, but my second would be longer. And so I could, I know, it's weird.
Yeah.
It's weird.
It's weird.
So like time would appear to pass normally for me, but for you it would appear to pass normally for you, but if you were to look at what was happening in my spaceship, time would be passing super slowly for me. So
this is very weird and very interesting.
it's very weird. So this is all about relativity, right? Like this is, it all stems from the fact that the speed of light is constant and has to be constant in all reference frames. So the speed of light is about 300,000 kilometers per second. So if I'm sitting...
100,000 kilometers per second.
Yes, very fast. Yeah, and nothing can go faster. That's like the universal speed limit. Like nothing is allowed to go faster than that.
Can I interrupt?
Oh, you can try. Go ahead.
So you told me that
Yes.
black holes can even bend light,
Yes.
or can what is the exact word that you used?
They are so gravitationally powerful that they...
Light cannot escape them.
Yes.
Yeah.
So that means that to
Can
escape
it slow down light?
it doesn't slow down light, it just bends it back. So you know how like, you throw a ball in the air,
Yeah.
it goes back to the earth. If you had like the biggest muscles in the world and you were able to throw your ball so fast that it would go into space, it would go in a straight line and it would escape, right? If you were to then have a black hole, something that is so gravitationally strong that even if you were to throw this photon at the speed of light, it would not be fast enough to be able to escape that gravity. It would go up and come back down. So this light is like trapped inside that black hole.
Okay.
It's just like circling around inside the black hole, essentially.
Interesting.
Yeah, it's pretty weird stuff, yeah. So, I mean, a lot of this is just like, I don't know, we've measured it, and it is the most accurate model of the universe we have so far, this relativity, this idea that, lengths aren't fixed, time isn't fixed, that gravity bends, the path of objects. It seems very weird to us, right? Like it doesn't make sense based on our everyday experiences, but it is stuff that we've measured in the universe. So like we've measured the path of light bending due to very massive objects. We've measured, lengths changing in different reference frames. We've measured time changing in different reference frames. So it is real. It's just very strange.
There were objects, man-made objects, that were able to achieve the speed that is greater than speed of sound.
Yes.
Supersonic.
Yeah.
We had supersonic planes that were discontinued. Right? It would take from US to France or UK maybe 1.5 hour, 2 hours max.
That was the Concorde, right?
Yes, the Concorde. And it was discontinued in 2004. We achieved a milestone that we can make up an object that can go beyond speed of sound. Not today, but in future, is it possible we can achieve this milestone of going beyond the speed of light?
No. It's a physical speed limit. It's like one of the rules of the universe seems to be that you cannot go faster than the speed of light. So just keep in mind, the speed of sound compared to this, or the speed of sound in air, we should say, compared to the speed of light is very, very small. It's what, 300 kilometers or 300 meters per second, something like that. So not even a kilometer per second, I think. It's about a third of it. Yeah, that's right. Because so you know when there's a lightning storm, and the lightning goes off in the distance, and then you count 1, 2, 3, 4, and then you divide by 3 to figure out
5 seconds.
Yeah. So like if it's 6 seconds away, then you know it's 2 kilometers away, and that's because it takes. Because light only travels about, I don't remember the exact number, but is about 300 meters per second. So that's approximately 3 seconds per kilometer. So it takes sound, sorry. Did I say light? I meant sound. It takes sound 3 seconds to travel 1 kilometer. So if you see a lightning go off and then you hear the thunder, the sound is traveling much slower to you than the light is. The light is almost instantaneous. Like if it's traveling 300,000 kilometers per second, it's taking much, 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 much less than a second to get to us. If it's a kilometer away, you know, or just a few kilometers away. So you're counting because light is almost instantaneous and sound takes this whole amount of time. It's very fast compared to like how fast I can run, but like it's still very, very, very slow compared to the speed of light. Even our fastest spacecraft that are going through space right now are nowhere near the speed of light. They're not even close. So it's a very, very fast speed, and nothing that we know of can actually travel faster than that. Even like particles that we observe, which are very light, they should theoretically, if there wasn't this speed limit, go as fast as they wanted to, but they still go slower than the speed of light.
But there is no obstacle in between, in space.
Yeah.
So not on Earth, but in space, can we achieve that speed ever?
No. Not unless you're like warping the fabric of space-time itself, unless you're like doing something that allows you to shorten lengths in space. Then you might be able to, from like an external point of view, travel faster than the speed of light, or travel distances that you'd normally be able to travel at the speed of light in a faster time. But we cannot currently do that. And unless we design a way to like warp space-time itself, there's no way we'd be able to travel at that speed. Yeah. It's a bit of a doubter, I know.
Yeah.
But
I heard of this theory that we all live in past.
Okay.
Explanation was the moon you see is few seconds have already passed that event happened on the moon. So is it 8 seconds, something like that?
No, to the moon it's about 1.2 seconds, 1.1 seconds, something like that.
1.2 seconds.
Yeah, 1.2 seconds.
So with sun it is how much?
8 minutes.
8 minutes, okay.
Yes.
So we can just compare the distance of moon and sun in this way.
Yeah.
That
moon is much closer.
moon is much closer.
Yes.
So a ray of light that will take just 1 second to reach from moon to earth.
Yes.
It will take 8 minutes to reach from sun to earth.
Yes, exactly, yeah. So the sun is 150 million kilometers away. And if you measure
150 million kilometers.
Yes. And the moon is only about 380,000 kilometers away, give or take. And so since the speed of light is 300,000 kilometers per second, it takes just over a second for light to get to the moon, but then obviously much longer to get to the sun, or from the sun to us.
The theory I heard was we live in past.
Yes.
Right? So the sun we saw is 8 minutes already. In the time.
Yes, yeah.
The
Anytime.
stars we are looking at, if a star is some billion years, light years away, and if we see it and it collapses, we might come to know about it once, few decades have passed.
Well, if it's a billion light years away, we wouldn't know about it for a billion years.
For a billion years, yeah.
So anytime we're looking into space, we are looking into the past, yes. In fact, anytime you're looking, like even you and me, we're technically living, nanoseconds in the past. Because, it takes a little bit of time for the sound to travel from my mouth to your ears, right? It takes a little bit of time for the light from me to, bounce off the lights here and bounce over here and go to your eyes. And then what takes even longer is just the time it takes for your, the signal to be processed in your brain and for you to have a thought about that, right? So like even in our body, there's, I don't know what the number is, I'm not a biologist, but there is a few microseconds between like, a photon hitting your eye and then your optic nerve processing that and relaying to your brain and then your brain doing its thing and then, me thinking of a reaction to it, like that's still a few microseconds. And so even within our own bodies, you're living in the past. So yes, we are.
Okay, let's come back.
Okay.
Let's talk about the origin of universe.
Sure.
The Big Bang Theory, some people believe in Big Bang Theory. What is the reality? What is the reality according to you?
Well, okay, so...
Again, it's relative, so I'm saying according to you.
The Big Bang Theory states, it's a bit of a misnomer because we don't think there was a bang. We don't think there was a big noise or a big explosion. We just think there was a rapid expansion. And so what it states is essentially that the universe started off very hot and very dense and then has been expanding. In that objects in the universe and the space between them has been getting bigger and bigger as time has gone by. And it's not a matter of belief for this one. You look at galaxies that are very far away and they're moving away from us. You look at galaxies that are even farther away, they're still moving away from us and they're moving away from us even faster. So that means, and it's the same in every direction you look. So that means that at some point in the past, everything had to be much closer if everything's moving away from everything.
In every direction, you're saying?
In every direction.
So that means we are in the center?
No. Because if you were anywhere in the universe, it would also observe everything moving away. A good way to think of it is, let's say you have a balloon, right? We're gonna do a two-dimensional example on a three-dimensional surface. So you're on a balloon, you're just a little ant, and there's a dot on the balloon, and then it's like a polka dot balloon, let's say. So you're sitting on one of the dots, and then as the balloon inflates, all of the dots seem to be getting farther and farther away from you. And the farther dots would appear to be moving faster away from you than the closer dots. Because you can imagine they're just moving this much, but these ones are moving like that much. But if you were to get off your little dot and go to another dot and watch the same inflation happen, you would notice the same thing. So it doesn't matter where you are in the universe, you would observe everything moving away from you and the farther things moving faster away from you. But it doesn't mean that anything is at the center. So we don't think that there is a center to the universe, we just think that it's infinite in every direction and you just go in one point and on a grand scale you'd experience roughly the same thing.
Universe is infinite.
Yes. That's what we've measured so far. It's not infinite in time, but it is infinite in space, coming back to our time and space. Because it had a beginning, approximately 13.8 billion years ago, but if you go in any direction, like in space, you would never come to the end of it.
What is the farthest object we have observed?
Oh, geez. Well, I guess technically it's not an object, but the farthest thing we can observe is the cosmic microwave background, which, coming back to the expansion of the universe, it was one of the final pieces of evidence that proved the Big Bang Theory, or, it vastly supported it. So what it is the leftover light from when the universe was very, very hot and very, very compressed and very, very dense. So if you wind back the clock and you go backwards in time, you know, you have stars, you have galaxies. If you go back in time, there was a time when the galaxies hadn't formed yet and the stars hadn't formed yet. And everything was just this sort of gas that was floating around. If you go back in time farther, this gas was very, very compressed and very, very hot, and it was like a plasma. So that's where it's so hot that the electrons are separated from the protons and the atoms. And everything's just buzzing about, and that means that light would not have been able to travel very far because it would have just been bouncing between these electrons that are floating around everywhere. It was very chaotic, like my life. But you wait for you know, the universe to expand a bit, so going back forward in time, then the universe cools down enough that these electrons recombine with their atoms. So then you don't have all these electrons that are floating around everywhere, getting in the way of the photons of light, and this light can all escape at once. And so that's what we're observing when we observe the cosmic microwave background. It's this point when all of that light was released. And so it's also at a point when the universe was very, very smooth and very even, and there were these very slight denser areas, but it was only like 1 part in 10,000. It was very, very slight. And then gradually over time, those slightly denser areas would have collapsed under the force of gravity and become like the first galaxies and the first stars, and then, you know, evolved into the universe we have today, where you do have like these clumpy, rich, denser regions and like vast empty regions, where it's all sort of like the cosmic web, the big spongy shape. I don't know. Yeah. But yeah, so it's not that, you know, whether or not you believe in the Big Bang, really, because there is a ton of evidence related to that. But yeah, so that's the furthest thing you can see. In terms of the furthest, like, distinct object, we've observed like the very first galaxies that formed. We call them quasars. And what you're actually observing, quasars, yeah, which stands for something. Doesn't matter. Quasi-stellar radio objects, something like that. So basically, these are new galaxies that have these supermassive black holes at the center of them. So we think that every galaxy has a big black hole at its center, just like our galaxy does. And back when the universe was hotter and denser, you had a lot of material that would have been falling into these black holes, and spiraling around the black holes. And as time went by, these, you know, black holes became much less active, and you have some that are more like the ones we see today. But in the very early universe, you could see these very bright objects called quasars, where it's basically just the material going around these black holes is glowing very brightly, in radio generally. Yeah, okay. So those are the farthest things we can see is quasars.
What is the furthest man-made object that has gone? I think it was some telescope?
No, it's the...
Some camera, this Hubble telescope or some...
No,
no?
Hubble is so close compared to...
No, not Hubble, but
yeah.
There was some other one. Voyager 1 maybe.
Voyager 1? Oh, yes. That's not a telescope, though.
Oh.
So yes, the farthest man-made object from the Earth is Voyager 1. We've put a lot of stuff into space. That's the one that's gotten the farthest. It's currently on the order of 20 light hours from Earth.
That's it?
That's it. So it's not even a light year away. And if Voyager...
Not even a light day away, I would say.
Not even a light day away. Almost a light day, not quite. So it takes about 20 hours for a radio signal to come from Voyager back to the Earth. But yeah, so that's the farthest man-made object. And so in what, 50 years, almost 50 years?
Oh God.
45 years? Wait, 1977 was when it was launched. That's as far as it's gotten. And if it was to continue at the speed it's going, and if there was a star that was, 4 light years away and it was pointed in the right direction, it would still take tens of thousands of years for it to get to even the closest star, which is like 4 light years away. So, yeah.
Okay.
So that's just to give you an idea of we have not touched the universe yet. We've touched our very close neighborhood. Actually, I think that's That's it right there. That's fun. Yeah, we've touched, like just our neighborhood, our very, very close neighborhood. But we have not been into the rest of the universe.
We have started, I would say.
Yeah.
That means.
I mean, we get to. Let's not like sell ourselves short. Like getting something to the edge of our solar system is an amazing feat, but it's not very far compared to the size of even the nearest star to us.
Talking about the size of universe.
Yeah.
Let's compare, and I think you can compare it in the best way possible. What is the size of a solar system, a galaxy, universe, and our Earth, Moon, and this
right
in this area?
Okay, so let's start small. Let's start on the Earth, right? So the Earth is what? A few thousand kilometers across. I think it's 10,000 approximately in diameter, order of magnitude. The distance to the moon, if the Earth was this big and the moon would be about this big, and the two would be like this far apart. So that's just the Earth moon. If we were then to shrink that down again, so like if the Earth's an inch, then the distance between them would be just over a couple of feet, let's say. The distance between the Earth and the moon compared to the distance to the sun, it would be like a little tiny, like 1 millimeter, let's say, to like 1 meter, maybe not quite that much. Let's say half a meter, just to be fair. Okay. But like it's these distances, like even that little distance between the Earth and the moon is very, very small, even though it's like larger than any distance we could ever travel on Earth.
So, 350,000 kilometers.
Yeah, so that's about, let's say 350,000 kilometers between the Earth and the moon. And then between the Earth and the sun is 150 million kilometers. So that's like 1 centimeter to a kilometer or something? Yeah, roughly.
A centimeter to a kilometer?
Yeah, 100,000 to 150.
Something like that.
It's 1,000 times, it's 1,000 times, approximately, 500 times.
If not more than that.
Yeah, it's 500 times bigger than, let's say order of magnitude. Yeah, so it's 500 times more between the Earth and the sun than it is between the Earth and the moon.
So 1 centimeter to a kilometer around. Now
let's say a meter to a kilometer.
A meter to a kilometer. Yeah. Okay. Now let's.
It's 500 times.
Let's make sun to 1 meter.
Yeah.
What's beyond? What's 1 kilometer now?
Oh geez. So the nearest star to us is okay. So let's just look at our solar system first. Let's look at our solar. Okay. So we'll call it 1 astronomical unit, because that's what it's actually called. The distance between the Earth and the sun is 1 astronomical unit. Okay. The distance to the farthest planet, which is Neptune, is about 30 times the distance between the Earth and the sun. So that's 30 astronomical units. And to give it in light times, it takes light about 4 hours to go from the sun all the way out to Neptune.
Before we touch down more than beyond Neptune, I would like to ask, why was Pluto removed?
Oh gosh, Pluto. So Pluto was considered a planet until what, 2003, I want to say, approximately?
Something like that.
Something like that. Anyway, it doesn't matter. Maybe 2006. It's one of those two dates. But the reason why it's not considered a planet anymore, it's still considered a dwarf planet. But around that time, we started to discover other objects that were of a similar size to Pluto, but there was a lot of them. And they're all in this like region called the Kuiper Belt, which is very, very far away. It's just past the orbit of Neptune. And you could start to find like all these little like Pluto-like objects. Now Pluto's still, I believe, the biggest of all of those, or at least the second biggest. There's another one called Eris, which is about the same size. But we started to find all these objects in that area, and we're like, oh, this is actually a debris field called the Kuiper Belt. And so this is just leftover material, essentially, from the formation of the solar system. And just to give you an idea, like, none of these objects are very big. Like, we have, the Earth, we have Jupiter, which is like, you could fit 1,000 Earths inside of Jupiter. You could
1,000 Earths.
Yeah. Pluto is like this little guy who's probably, it's definitely smaller than the moon. And, it's not a large object at all. It's only a couple hundred kilometers across. It's very, very small. And so we started to discover all these objects. And so we're like, we're gonna now have to either include all these objects as planets, or start to classify Pluto and these other similar objects as something else. And so instead of making school kids learn like 50 planets, we decided to demote Pluto into a dwarf planet. And so now the definition of a planet is something that is large enough to be spherical in shape, because its gravity pulls it into a sphere. It's something that goes around the sun, and it is also something that has cleared its orbit. So it's something where there are no other objects, essentially, of a similar size in the same path as it around the sun. So Pluto doesn't fill that last criterion because there's a whole bunch of other objects very similar to it in the Kuiper Belt, so it has not cleared its orbit. So that's why Pluto is not considered a planet, but it is still a category of planet-like object called a dwarf planet. So it's not, Pluto doesn't care, right? It's just us who cares.
Coming from India, it fascinates me.
Yeah.
That we have been doing, like, worshipping. In India, we worship planets. We have been worshipping, so we have this, gathering, religious gatherings.
Sure.
Where we worship 9 planets.
Okay.
And we have been worshipping this kind of worship for 1,000 years, if not more. How did we know that? Like how? And they are not just in India. You'll see some geological surveys happening in Egypt, then in south of the African continent. We have seen such.
Yeah. That I cannot speak to necessarily, because obviously I'm not an expert in any sort of religion.
No, not talking about religion, but
yeah.
In different parts of Earth, we have seen such evidences.
Yeah.
That
so again, not an archaeologist either, right? So of all the planets, the ones you can actually see with your eyes, there's Mercury, Venus, Mars, Jupiter, and Saturn. You cannot even see Uranus and Neptune with your naked eye. Maybe Uranus, like, if you're very lucky. But Uranus was discovered in the 1800s, or no.
Which planet can anyone see easily with naked eye?
Mercury, Venus, Mars, Jupiter, and Saturn.
Okay.
And Earth, because if we look down.
Okay.
Yeah.
How do we check the sky for these planets? Because many have not seen, including me.
Sure. Okay, let me just finish the last thought.
Yeah.
I wasn't done yet.
Please.
Okay, so those planets we can see with the naked eye. Uranus and Neptune were detected with telescopes. Neptune was actually detected because a French mathematician noticed variations in the orbit of Uranus, which meant that maybe there was another planet out there. And so he sort of detected where it should be, and lo and behold, there was Neptune. Pluto was discovered more or less by accident in the 1930s. I think, it was not something that was powerful enough to have, or it's not something massive enough to have been able to modify the orbits of other planets, because it's very, very tiny. But it just happened to be something that was in the telescope, and then they looked at it for a while and was like, oh, that's actually an object that's going around the sun. Let's call it Pluto. And so chances are that any ancient civilization that counted more than 9 planets, or counted more than just the planets you can see with, so more than the 5 planets you can actually just see with your eye, likely they were looking at something else as well. So maybe they're counting the moon as a planet. Maybe they're counting, some star as a planet. Maybe they're counting something else as a planet. But the chances of them being able to see, those really far away planets that we currently can't see with the naked eye, like of them counting them as one of the planets, is very unlikely. So my guess would be that they're just counting something else. But again, not an expert at archaeology, so I can't say for sure.
Let's come back to the let's come to the next question, and then we'll go back to the time we were measuring.
Sure.
Okay, so my next question was that I asked you about.
Was it how you actually observe planets in the sky?
Exactly.
Yeah.
For a normal person.
Right. So the planets, because they're close to us and generally are pretty big, are pretty easy to see by the naked eye, just as extra bright stars. So in particular, Venus and Mercury, you only ever see them, because they're closer to the sun than we are, you only ever see them either right after sunset or right before sunrise. And I'm not sure on which side they are right now, but like if you're looking at the western sky right after sunset and you see something that's incredibly bright, that's close to the sunset, and you don't see any other stars around it, and it's not an airplane, then it's probably Venus. And if you see something that's a little bit fainter, that might be Mercury. I find the easiest way is just to use one of those apps, that tells you where the things in the sky are. And usually they're very bright that you can pick them out from other things. But one of the main tricks that we use for observing planets is that planets tend not to twinkle. So you know how stars, you're looking at them on a beautiful clear night and everything's going, it's like twinkling a little bit, right? So that's because of our own atmosphere. So we have all this air surrounding us, and especially on hot days, air is very turbulent. It rises and comes down and moves around a lot. And that movement in the air causes the light that's coming from stars to sort of bounce around. So you can have, like a very distant star, it sort of jiggles its light around. And this is because stars are so far away, as we've already discussed, that whenever you look at a star, it only looks like a point of light. Usually, they're so far away that you can't resolve the size of the star. Like you see it as a point of light, but you can never figure out how wide it is. Planets, on the other hand, are much closer, and so when you look at a planet through a telescope, you're actually looking at a circle. You see like a little disk. So like when I look at Jupiter through a telescope, it basically looks like a white circle with some dots around it, which are the moons. And like if you look really closely, you can see some bands, which are the cloud bands and all that stuff. So that means that because these are wider things, as the light comes through the atmosphere, it doesn't jiggle around as much. So planets tend not to twinkle as much. And so usually if you see something bright and then you see something bright next to it and one of them is twinkling and one of them isn't, then likely the one that isn't is a planet. But that's not always a hard and fast rule, but that's usually a good way to tell them apart. And then planets like Jupiter is very, very bright. It's brighter than most stars that you'd look at. Venus, as I already said, is very, very bright. It's the brightest object you can observe in the sky besides the sun and the moon.
Jupiter.
Venus.
Venus.
Jupiter is, I think there might be one star that's brighter than Jupiter sometimes, but it's also very, very bright, brighter than most stars. And then the other planets are a little bit fainter, but using an app or something, you can usually find them.
There's a star, Eris 1, something like that.
A star?
Yeah.
Eris?
Eris 1.
Eris 1?
I've heard about this star. They say it's very clearly visible. It's not in our system, but it's clearly visible.
Is it Sirius? I don't know. There's a lot of stars. I don't know one called Eris.
I don't remember.
There is a dwarf planet called Eris.
Okay.
We cannot see it with the naked eye because it's about as far, or I think it might be even farther away than Pluto is. I don't know of any others. Nothing called Eris, really.
Okay.
Yeah.
So these are very big telescopes that we are looking at. Some are home telescopes, the
Sure,
small
yeah.
ones.
Yeah.
Are they useful? Like, can
Yeah, totally. Even in even in a set of binoculars, you can look at the moons of Jupiter, you can sometimes see the rings of Saturn. If you're just getting started with astronomy, one of those little like tabletop, ones you can get on Amazon, you can still observe very cool things with it. So for observing the planets, a small telescope is great. You can see the circle of the planet. When it's Jupiter, for example, you can see the 4 Galilean moons of Jupiter, which are, I said Jupiter and Jupiter pops up on there.
Wow. It's going like us only.
Yeah. Anyway, so when you're looking at Jupiter through a telescope, you can see Jupiter itself, and you can also see 4 of its moons, which are called the Galilean moons because they were discovered by Galileo. And they basically look like 4 little dots of light that are surrounding Jupiter. When you're looking at Saturn through a very small telescope, you can still distinctly see that sort of ovoid shape because you can see the rings. And if you have
a small telescope, you can see the rings.
Yeah. There's various stars you can observe where you can like see the colors of the stars, or you can see a binary star, or things like that. So definitely with a nice, or with a little telescope, you can see things. And even in the city, like even in Toronto, you can see some nice stuff. Yeah. And then if you want to splurge on, a 4-inch to 6-inch to 10-inch telescope, then you can start to see cool things like clusters and galaxies and nebulas and all that fun stuff. It's harder to see those objects in any area where there's light pollution, but if you can get outside the city where there's less lights, then it's better.
Okay, let's go back to the distance we're measuring.
Sure, right.
So we went till Sun?
Yeah.
Let's go beyond.
Okay, so we went from the Sun to Neptune.
Sun to Neptune.
Yeah. So then there's the Kuiper Belt, which is this area of debris that's basically where Pluto lives. The Kuiper Belt extends to about 50 to 70 times the Earth-Sun distance. And then you have Voyager 1 and 2 that are even beyond that. And then you have, and they're this 20 light hours.
Voyager 1 to have crossed the Kuiper Belt.
Yes, yeah, it's farther than that, yeah.
Quite a good achievement.
Yeah. So, yes, it's a pretty cool achievement. It's actually at a point called the heliopause, which is this point when the stream of very energetic particles that's coming off of the sun, which we call the solar wind, sort of meets up with all the streams of particles that are coming from all the other stars, the cosmic winds essentially. They sort of balance each other out, and you reach this point called the heliopause. So it's basically a very quiet area where there's no winds coming from other places, and it's actually crossed past that. So this is like one way we could define the edge of our solar system, where we could say that Voyager 1 and 2 are actually on the other side, outside of our solar system. But there are objects even farther out than that are still technically considered to be part of our solar system, and those are part of the Oort cloud. And that's this big cloud of debris that extends out to almost a light year, where you have these very, very long period comets that live, and then other random objects. And so these very long period objects, they might have a period of like several thousand years or several tens of thousands of years. So they live in this very, very distant place. They're very slowly going around, and then something jostles them and they start falling towards the sun, and then they have this very long elliptical orbit where, for maybe a couple of months, they're very, very close to the sun, and they sort of get shot out again, and they're then back in the Oort cloud where they travel for thousands of years, and then they come back close to the sun.
Same as the Earth's orbit is elliptical, it's not circle.
Yeah, but these are like really elliptical. So the Earth's orbit could be approximated as a circle. It's very, very close to one. It's slightly elliptical, like it's a little bit farther away, or a little
Making it winters and summers. And
no, that's something else. We could get to that later.
Okay.
So the sun, we're actually farther away from the sun right now than we are during the winter.
No, that's what we call elliptical.
Yeah.
That's what.
But it's warmer right now than it is in the winter. So we're farther away from the sun. So it's not because of the elliptical orbit of the Earth that we have seasons.
Okay.
But we can get to that later.
Sure.
anyway, so these comets have these very, very long periods where they're very, very close to the sun, traveling very quickly, and then go back out and are very, very, very far away. And so, for example, Hale-Bopp, do you remember that one? It was from the late 90s. It came close to the Earth. It was very, very bright. But that comet had a period of like several thousand years. So it only came towards the Earth for a couple of months and then is spending time very, very far away from the sun for like, a couple thousand years or whatever.
A couple of thousand years.
Yes, yeah. So that's the Oort cloud, and we're now at about 1 light year from the Earth, let's say. The very edge of that would be about 1 light year. And then the closest star to us is still like 3 more light years after that.
The closest star to the...
Yeah. So the closest star to us is Alpha Centauri. It is actually a triple star system. There's Alpha Centauri A, B, and then Proxima Centauri. And so you have these 2 stars that are about the size of the sun that are going around each other, and then a third tiny one that's sort of going around both of them. And this tiny one currently in its orbit is closest to the Earth. So Proxima Centauri is technically the closest star to the Earth, but you can just say the Alpha Centauri system. And so this system is 4 light years away, approximately, and that means it takes light from those stars 4 years to travel to the Earth. So
if something happens to that star today, we'll know about it after 4 years.
Yes, exactly. And that's just the closest star to us. So if you imagine the sun is a grain of sand, and the next star over is a grain of sand that's 1 meter away. The coating on top of the grain of sand would be the solar system.
Oh, wow.
Yeah.
This is interesting.
Yeah.
Let's go beyond.
Okay.
Let's go beyond.
Okay, so then we can sort of think about our neighborhood of stars. So the closest star is 4 light years, which in kilometers is about 10 trillion kilometers. It's either 10 trillion or 10 quadrillion. I always get the...
I thought you're decreasing, maybe 10 million or 10 billion.
No. Bigger. Yeah, so anyway, 1 light year, is, 4 light years is the closest star.
And we have not even reached 20 light hours till now.
Yeah, and we have not even reached 20 light hours, exactly. Yeah.
Way to go.
Yeah. So that's physical objects that we put into space, but we have been emitting radio signals into space, right? So we've been emitting radio signals into space for what, not even 100 years. Let's say 100 years, roughly. So that means that the farthest any radio signal has gotten from the Earth out into space is about 100 light years from the Earth. So you could sort of imagine a sphere 200 light years across that, which is all of the influence of humanity, essentially, the farthest that any radio signals have ever gotten. So you have this sphere. It probably contains, I think I calculated once, it contains roughly on the order of a few hundred stars, maybe up to 1,000 stars, I can't remember exactly, but yes. So it contains like several hundred stars. So all of those stars, if there's planets going around them, they could have had some sort of signal arrive to them from the Earth. But that sphere, compared to the size of our galaxy is about 100,000 light years across. So 200 light years versus 100,000 light years across, that's 1,000 times bigger, roughly, right? So if you thought of the galaxy as a dinner plate, it would be like one little grain of sand on that dinner plate would be all of humanity's influence on the universe. Yeah, so even the farthest that we've been able to send signals into space, even that is insignificant compared to the size of just our galaxy. And then our galaxy is 100,000 light years across. We have
it in a plate?
It is actually kind of in a plate shape. It's a spiral galaxy, right? So the Milky Way is sort of shaped like a frisbee, I guess, or a plate, with these spirals that go around, right? You've probably seen pictures of just that classic spiral galaxy. So It's roughly that shape, and you could sort of imagine that it's 100,000 light years this way and maybe 1,000 light years that way. So it's thin and wide, right? And then we have a few littler galaxies we call dwarf galaxies that orbit around the Milky Way. So they're basically these like clumps of stars. A couple of examples are the Small Magellanic Cloud and the Large Magellanic Cloud. Those are two you can actually see from the southern hemisphere with the naked eye in like very clear sky conditions. And these two galaxies are several tens of thousands of light years away, but they're just going around. I think they're 100,000 light years away.
They're around Milky Way.
Yeah, so they're going around the Milky Way, sort of like planets orbiting the sun, but these galaxies orbiting our galaxy, yeah.
So our galaxy is also big enough to get orbited by other galaxies?
Yes, little guys. I mean, little. They contain, you know, our galaxy contains probably around 100 to 300 billion stars.
300 billion stars?
Yes. And these galaxies are much smaller and only contain maybe a million. And one of them is Sun? One of them is the Sun, yes.
300 billion stars?
Yes.
That means each star has their own planets?
Not necessarily. Some stars are too big to have their own planet systems. Like if they're very, very large stars, they're very energetic, and then they'll basically burn away any planets that are around them. So those don't tend to have planets. Typically, stars that are in binary systems, if there's planets that form around them, they tend to get shot out because of gravitational interactions with the two stars. Mm-hmm. So those wouldn't typically have planets. Yeah, so not all stars have planets, but we think that most of them do. So, yeah, if you have 300 billion stars in our solar system, in our galaxy, not in our solar system, then you have maybe half of those, let's say, that have planets. And then we think that in our galaxy that there's probably approximately 9 billion rocky planets that are about the size of the Earth that are going around their stars as well. So, that are in the habitable zone. So sort of Earth-like planets.
9 billion.
Yeah, in our galaxy.
Interesting.
Yeah.
Okay, let's go beyond this.
Okay, so our galaxy, let's now shrink it down to like a contact lens.
Okay.
So it was a dinner plate, now it's a contact lens. Mm-hmm. The nearest big galaxy to us is called the Andromeda galaxy. It's about the same size as the Milky Way, maybe a little bit bigger. And it is about 2.5 million light years away. So when you're looking at that object in space, you're looking at it as it was 2.5 million years ago. And it would, if it's also shaped like a contact lens, they'd probably be about, I don't know, half a foot apart, let's say.
That's it?
Yeah, they're pretty close relative to their size.
Okay.
So you think 100,000 light years across to 2.5 million, it's only 10 times as much, roughly 25 times as much. So, 1 centimeter to 25 centimeters kind of thing. Mm-hmm. So yeah, let's say they're 25 centimeters across if they're two little contact lenses here. But then these are only this is like our closest full-size galaxy. These two are only a couple of like our local group of galaxies, which includes galaxies that are like within about 10 to 15 million light years of the Earth. So then we shrink that down again, and we have like a few more galaxies that are now in this cluster of galaxies that makes up our local group of galaxies, and they're sort of gravitationally interacting as well. These
constellation.
Sorry?
That's the constellation?
No. So constellations are only stars within our own galaxy.
Okay.
And those stars are all within about 1,000 light years.
Mm-hmm. Okay.
So the constellations are much closer than any of this so far.
Okay.
Then you have the Virgo cluster, which is a huge collection of like thousands of galaxies that are all going around each other. And this is like several 100 million light years away. And then you look at, there's a whole bunch of like super clusters of galaxies. I can't remember what the most recent one that was discovered is called, but the last one I remember is called Laniakea, which is even bigger than the Virgo supercluster. It's like a cluster of superclusters. So now we're talking about, billions of light years across. And then we get to very distant galaxies. The farthest galaxy we've ever seen is on the order of 13 billion light years away, I think.
13 billion light years.
Yes, very, very far. So, yeah, the farthest galaxies we can see are billions of light years away. That means their light has taken billions of years to reach our eye, which means when you're looking at them, you're looking at the universe as it was when it was much younger, which is kind of cool.
We don't even know that if that galaxy exists today.
It might not. Yeah, there would be no way to know. Even looking at stars in our own galaxy, there's some that might have gone supernova and we won't know about it for hundreds of years, right? So, or thousands of years. And then you look at the edge of the visible universe, and that's 13.7 billion light years away. That's the farthest we can see. That's that cosmic microwave background. And that is the furthest distance we can see, but we think that the universe is infinite beyond that. That's just because it's just taken this amount of time for that light to reach our eyes. So.
And what's beyond that?
More galaxies,
Is there an end to the galaxy? Is there an end?
We don't think so. We think that it would just keep going on forever. If you were somehow able to travel faster than the speed of light and go through the universe at these speeds and be able to see it all in an instant, we think you could just keep going forever and ever and ever and ever and ever, and you would never reach the end of it.
A very dumb question for you, but for me, informative one. When we send missions beyond Earth, how is it checked that, because in space there's a lot of debris revolving around, because you never know when something blasts and something can happen. Yeah. A lot of stars emit energies, a lot of planets, a lot of these I would say stones are revolving around. Asteroids are there. How is it possible that Voyager 1 has not hit anything?
Right.
How do we determine the direction of where it is sent?
So, currently the most dangerous place to get through is just the space junk that's around the Earth, right? All of the debris that's left there. And for the most part, the larger chunks, people tend to track. So we try to keep track of all the little pieces of debris that are around the Earth. So that's the most dangerous part. In 1977, when Voyager 1 and 2 were launched, that was not as much of an issue. But if you keep going into space, you then have the asteroid belt, right?
Yes.
So between here and the asteroid belt, space is very empty. When you get to the asteroid belt, it's still very empty. Even though there are probably billions of objects in the asteroid belt itself, the chances of us hitting something are very, very slim. So just to give you an idea, if you collected all the material that was in the asteroid belt and you just clumped it up into a ball, it would still be less material than you have in the moon. So it's very, very diffuse. There's a lot of objects, but the chances of you hitting one are still pretty low, right? And so when Voyager 1 went through the asteroid belt, it didn't have much to worry about, because if you were sitting in the asteroid belt and you were sitting on one asteroid, you wouldn't be able to see the next one. It would be so far away, right? And these objects are only sometimes just a few hundred meters big, right? So they're pretty small. Maybe that is the reason that not much asteroids they don't hit Earth. Well, not currently. There was a time in the past when, there were lots of asteroids hitting the Earth, but they're just, there's a lot of them, and if something jostles them out of the orbit and they come close to Earth, then that's a problem. But just passing through the asteroid belt is not necessarily a problem, if that makes sense. And then getting to the Kuiper Belt, it's a similar situation. Now, let's discuss about types of galaxies you were talking about. Oh, sure. So the Milky Way, which we've already talked about a bit, is what we call a spiral galaxy. So Spiral galaxies tend to be like these flat disks that have spiral arms, and generally they tend to be the types of galaxies where there's lots of new stars forming. So there's lots of gas and dust in the spiral arms that then form new stars. The other main type of galaxies is called elliptical galaxies, and these are basically shaped anywhere between a sphere and like a football. So they're sort of like these big clumps of stars that are sort of in this rounder shape. And these are tend to be older in that the star population in them is a little bit older because there isn't a lot of new star formation that happens. So you don't have a lot of new stars popping in, and those tend to be the sort of bluer ones. So these galaxies tend to look a little bit redder. So you could sort of think as spiral galaxies as new stars are forming, they're flat, they're disks, they look a little bluer, and then these elliptical galaxies, they look a little redder, and then there's not much gas and dust, and there's not a lot of new stars that are forming. And then you have these weird types of galaxies that are called irregular galaxies, and those essentially happen when two other galaxies crash into each other or interact in some way. And there's some examples of this. There's the antenna galaxies, where you can basically see these two cores of galaxies and then like these weird streams coming off that are tidal streams due to the gravitational interactions between these two galaxies. And then you have some where two galaxies have already merged, so you have like a denser clump in the middle and then like this weird ring of stars around it.
How often this phenomena is that galaxies collide and...
I mean, often enough. Enough that we see like lots of examples of it in the universe. It obviously would have happened more in the past than it would happen now. So you tend to see more of these irregular galaxies as you look like farther back into time, because that would have been when more galaxies are closer together and therefore can interact more. But for example, the Andromeda galaxy that we already talked about, it's on a crash course with our galaxy. Mm-hmm. So in several billion years, the Andromeda galaxy will crash into and merge with the Milky Way galaxy, and then we'll have like some weird
phenomena going on.
Yeah, we'll have some weird hybrid galaxy, and so it won't look as these two pretty nice disks. You'll look at like this weird clumpy thing with tails coming off and stuff. So those are the three basic types of galaxies, are just like these spirals, these ellipticals, and then weird irregular ones that are due to galaxy mergers.
We have these beautiful photos of galaxies, of stars. This, I would say, colorful, red, blue, green, some different shades.
Yeah.
Is it all visible through the telescopes?
No, not always. So a lot of those images, they use types of light that we can't see with our eyes. Mm-hmm. So, we can see visible light. We can see red to purple or violet. And that's the wavelengths of light that we can actually see with our eyes. But beyond that, on the red side, there's infrared, there's microwaves, there's radio, and then on the violet side, you have ultraviolet, and then X-rays and gamma rays, and those are very, very energetic light, and those are very not energetic light. And so a lot of those pictures, you're looking at either infrared or ultraviolet or one of those different types of light. So for example, the James Webb Space Telescope, which has been sending back all these beautiful images, it's been taking pictures mostly in the infrared. And so when we see one of these pictures, these are things that we would not actually be able to see with our eyes. Mm-hmm. These are things that are being revealed to us through this ability to detect light that is beyond that spectrum. So, and that allows us to see features that you wouldn't be able to see otherwise, because so you have a lot of dust in our galaxy, right? And visible light can't go through this dust, but infrared light can. And so if you're looking at infrared light, you can actually see beyond a lot of these dust clouds that you wouldn't be able to see through with just visible light. So you get to see all these new features, all these new stars and things that you wouldn't be able to see before. So that's one of those advantages. And then, we have lots of pictures in X-rays and radio waves and all over the place. But yeah, so we're looking at the whole spectrum of light, not just visible light.
Let's talk about our own system.
Sure.
Let's come back.
Sure.
Most fascinating planet to humankind right now is Mars, and one of them was Saturn to me because of the rings and the planets, the moons. How many moons are there in Saturn? To give a prox number.
Last count, Saturn has over 100 moons, and I've lost track of the number. And those are just the ones we've detected. Jupiter has over 80 moons, but probably more because those are just the ones we've detected. Uranus and Neptune both have dozens of moons each. So there's hundreds of moons in the solar system, I'd say. Like Earth has one. Mars has two. Venus and Mercury don't have any moons.
Again, a theory came up that...
Sorry?
A conspiracy theory came up. I don't know from where.
Sure.
That it is possible that moon can be artificial satellite or something like that. It's too big to be artificial.
Yeah, the moon is about a ninth the diameter of the Earth, right? So imagine putting like 1/9 of the Earth into space, whereas we've put, the biggest thing we have in space right now is the space station, and that's like maybe 100 meters across? Whereas the moon is like thousands of kilometers across, or not thousands of kilometers, thousands of meters across, but yeah, hundreds of kilometers.
Even talking about ISS, our International Space Station.
Yes.
I think I have heard that it's most valuable object ever made by us. Like more than $1 billion were used. And not one country was able to afford that. So many countries came up and they made it up.
Yeah.
And right now, I saw this in news that there is possibility that space station might go off, and we are planning some other space station or something like that.
Yeah.
Is there a possibility?
I mean, all of these space missions have a planned end date. Like, sometimes they last longer than we expect them to, but there is a point where we're going to be like, okay, it's time for the space station to be done, and that's probably going to be in about 5 years. And at that point, it'll we'll probably put it into a lower orbit, and then it'll crash into the Pacific Ocean, far away from people as possible, and mostly get burnt up in the atmosphere. But yeah, that's just the reality of it. But what was the other part of the question?
Are you aware of this two astronauts that are stuck?
Yeah, I've heard about it.
Sunita Williams, one of them is of Indian origin. She's stuck in space for 50 days. Something like that. Or they have ability there to be there for 50 days more than that?
Yeah. Well, so I mean, the space station, there's astronauts who have been there for like a year, right? So they have enough supplies on the space station to support people for an extended period of time. So it's not that much of an issue, but yeah,
But why are we calling it that they are stuck there?
Well, because the capsule they went with, it had some malfunctions, right? And so they didn't want to send them back to Earth until they'd done like a full assessment of what the malfunctions were and repaired it to the best of their ability in space. Because you don't want to be sending people in the capsule that's going to fall apart, as it goes back into the Earth's atmosphere. So I think that was the main issue. I haven't kept up with the story, but that's what I understood from it.
You were also talking about stars. They get birth and they die. Now, many movies we have seen that stars falling apart, all that. How common is this phenomena as well?
Of stars falling?
Stars falling apart.
I mean, it happens to a certain degree at the end of their lives. So, okay, let's go into like the details of it. Yeah, life cycles of stars. So, let's say you're in space, you have this giant big blob of mostly hydrogen gas with some dust and other elements in there. So, there will be a denser area in that cloud of dust, and that will start to collapse under the force of gravity, and start to collapse more and more and more and more until it's like there's so much pressure and there's so much heat that something called hydrogen fusion starts. And hydrogen fusion is basically just hydrogen gas, the lightest of all the gases and all the elements. Two hydrogen atoms will, fuse together roughly to make a helium atom. I mean, there's a lot more that goes into it than that, but yeah, you basically end up with going from this hydrogen gas to this helium gas. So what happens during that reaction, during hydrogen fusion, is that it gives off a vast amount of energy. So one of these reactions obviously wouldn't, but you'd have trillions of these reactions going off. And so as soon as that hydrogen fusion starts, then the star starts to glow. It sort of pushes away those outer layers and becomes like an actual star. So throughout its life cycle, basically, you have this big ball where you have mostly hydrogen gas that's very, very hot, and then at the core of the star is where that hydrogen gas is fusing into helium. And so you have this sort of balance between gravity pulling in and wanting to fuse that hydrogen, and then the hydrogen fusing into helium and that giving off energy, which then pushes out. So it's in balance. Yes.
Sorry to interrupt. This fusion of hydrogen atoms, is it the same thing that we're talking about is happening in hydrogen bombs?
Yes.
The fusion of atoms?
Yeah. Mm-hmm. Yeah. So in a hydrogen bomb, which is clearly very explosive, you have that happening in the sun just at a much larger scale.
How many atoms are there in a hydrogen bomb compared to what is happening happening in a star?
I'm not sure, but it's
a million times?
Yeah.
Something?
So the sun is 2 times 10 to the 30 kilograms. So that's 2 with 30 zeros after it kilograms. And one of those bombs is I don't know, maybe 100 kilograms.
Yeah.
So
with 30 zeros?
10 with 30 zeros times more energy than that, let's just say. I don't know. I'd have to look at the actual numbers, but
beyond we can count.
Yes, it's a lot of energy that it's giving off. And that's enough to sustain that reaction for billions of years, right? So the sun is about 4.5 billion years old, and we expect that it will continue to fuse hydrogen in its core for another maybe 5 billion years.
But there is an end to this energy. So energy is, if something is emitting energy, it's cooling down, let's say, no?
Well, so the emission of this energy is what keeps the sun burning, essentially. It's what keeps it hot. But there is a point when you're going to get a buildup of helium in the core, because it's like ash building up, essentially, right? So you have hydrogen fusing, creating helium, and at some point, you won't be able to fuse any more hydrogen in the core because it'll just be too much helium in the way, essentially, right? And so what will happen is that very quickly, hydrogen fusion in the very center will stop. It'll still continue all around the edges of the core, but the core itself will start then collapsing a little bit because there's no hydrogen fusion to push it out, and it'll actually collapse in and get hot enough that you can start helium fusion. So then you have helium atoms getting squished together and forming carbon. And then, this keeps happening, and it depends on the mass of the star. So our sun is not the most massive type of star. And so we think that it will be able to fuse, it's fusing helium now. In maybe 4 billion years, it'll start to fuse this helium into carbon, and then the carbon into oxygen and nitrogen. But we probably won't go any farther than maybe carbon, right? Carbon or oxygen, maybe. And then once this helium fusion starts in the core, the outer layers actually expand outwards because of this new fresh burst of energy. So the outer layers expand outwards, and the star becomes something called a red giant, which is where basically, since the outer layers are so far from the core of the star, they sort of cool down so they look redder, and then the star balloons up to be very, very wide. And so for our sun, when this happens, it will actually extend out to just past the orbit of the Earth. So in 4 billion years, 5 billion years, the Earth is essentially going to be incinerated by the sun expanding outwards. So that's fun. But then if you have a more, and at that point, like, it'll continue fusing helium in its core for maybe like another 100 million years or so. And then eventually that no more fusion reactions will be able to happen because there'll be this buildup of carbon. And it won't be able to have enough gravity to fuse any heavier elements. So the outer layers will just continue to expand outwards into what we call a planetary nebula. And the core of the star will become something we call a white dwarf, which is just this very dense, hot remnant of the core of the star.
This is so fascinating.
And they're very hot, but yeah.
This is so fascinating. How these all phenomena happen, and we just know maybe just tiny bit about it.
Mm-hmm. Yeah. Well, what's even cooler is that when you have a star that's like maybe 8 times as massive as our sun, it can keep fusing those heavier and heavier elements. And so all of the elements, when they're fusing together, they give off energy which counteracts gravity that's pulling in, right? So when you get to iron, so that's like you're fusing, I think it's silicone into iron. That reaction takes in energy instead of giving off energy. So at that point, as soon as iron fusion starts, you're no longer pushing out.
Emit energy, you just absorb energy.
Just absorbing energy. And so what happens very quickly, like within a few seconds of this iron fusion starting, is that the core of the star itself will just collapse under its own gravity. And so the core will collapse about as dense as it can get. The outer layers will like start to fall in as well. And since they're falling in so quickly, and they'll get like superheated, and because they're getting heated so quickly, they'll just explode outwards into this supernova explosion, which is one of the most energetic phenomenon that we can observe. One supernova going off can like outshine an entire galaxy. So you can see like a galaxy and it looks like it just has a bright star that appears in it. All of a sudden, that's a supernova explosion. And there's certain stars that we see in the sky that if they went supernova, they'd be as bright as the moon in the sky. So it's like a very, very energetic phenomenon. And so then the core of that star, since it's collapsed as much under the force of gravity as it can either become what we call a neutron star, which is basically the densest state of matter that can exist. Where you have like all of the electrons and protons have fused together, and it's basically like into neutrons, which is why it's called a neutron star. And it's basically like the big nucleus of an atom, just made of neutrons. And just to give you an idea, they're usually about 1.5 to 2 times the mass of our sun, but would only take up about 15 kilometers. So they're like these very dense objects.
We have gone that far. We didn't compare the size of Earth and our sun.
Oh, that's true.
What is it?
So the Earth would fit into the sun about 1 million times. So,
wow.
Yeah.
So many stars are there. And as you told, this nebulas are created and stars just shrinks, I would say. A nice word to describe it.
Well,
they just shrink.
The core of the star just collapses. Yeah, like gravity takes over and there's nothing to push out against gravity. So it just falls in as much as possible.
Can call it a black hole?
Almost. So a neutron star is like the last step you get before a black hole. So I was sort of going to bring it around.
Okay.
Because when you have a neutron star, basically the only energy that's pushing these neutrons away from each other is a quantum force called neutron degeneracy pressure, and that's the last sort of bastion before gravity takes over completely. If you have an even more massive star with a more massive core, then gravity takes over completely, and even that neutron degeneracy pressure can't stop the star from collapsing in on itself completely, and so the core of the star then becomes this black hole, where it's so dense that nothing is pushing out against gravity, and you get like what is called a singularity, which is just this one point of infinite density. At least we think so.
Is it possible our sun will become a black hole one day?
No. So our sun is not massive enough to even go supernova and to become a neutron star. The star would have to be at least 8 times the mass of our sun. And to become a black hole, it would have to be around 20 times the mass of our sun. So that's these very, very massive stars that could become black holes.
Okay.
Yes. But our sun will not become a black hole.
This conversation is going on very interesting and amazing. Thank you for joining us.
Yeah, of course.
Let's talk about life beyond Earth.
Okay.
So, millions, if not, what if not? Billions of stars, if not trillions. And from them, billions are like sun. And if not hundreds and thousands of trillions of planets?
Yeah, I mean, in our universe, likely
possibilities are there.
Yeah, there's probably, trillions of planets that are just in the galaxies that we can see, right? Or probably even more. So we think, let's just focus on our own galaxy, because that's enough to think about. So we have, 100 billion stars. We think that probably a good portion of them have planets going around them. About maybe 9 billion of those are planets that are rocky and in the habitable zone, but then you have to think of, do they have plate tectonics? Do they have water? Stuff like that. So but statistically, that's just so many planets that there likely is, at least 1 or 2 planets out there, even our own galaxy, that have life on them. The chances then of it developing into intelligent life that can send radio signals out into space that we could detect is another thing. So the history of our universe is, over 10 billion years old, right? And our human civilization, where we've been able to send radio signals into space, is 100 years, right? No. And you know what? Like, the way humanity's going, we could blow ourselves up in like the next 100 years, right? The chances of us lasting for millennia more, maybe if you're really pessimistic, aren't very good. But if you're optimistic, let's say we last for a few more millennia. But I mean, human civilization will be so different in a few millennia from now that who knows if we'll even be using radio technology. Maybe we'll find something better. So that window of seeing other civilizations and them having a radio signal that like passes by us in the amount of time that we're able to detect it is also very slim. So there's just like a timing thing, right? Like if there was a civilization that came to maturity 100,000 years ago and then sent out a bunch of signals into the galaxy, but then they developed some huge bomb that blew themselves up 1,000 years later, then that was still 9,000 years ago, and we never would have had a chance to detect their signals, right? So, like, what I'm trying to say here is that there are likely there's probably a lot of life in our galaxy, and definitely in the universe. There's probably other intelligent civilizations, even in our galaxy, that might have existed at some point, or that may exist in the future, but the chances of us running into them are very slim. Because of this time thing, and because human history compared to the history of our galaxy is so short, and also because you're limited by the speed of light, right? Remember I said earlier that the amount that we've influenced even just our galaxy is like a grain of sand on a dinner plate. Like, our radio signals have not gotten very far. And so within that, maybe there's a few hundred stars out of 100 billion stars. So like, I do think that there's probably life out there somewhere, and likely intelligent life, and maybe even life we could talk to. But the distances between stars and between galaxies are it's so vast, like unimaginably vast, that the chances of us running into them seem very slim. So that's my sort of hot take on that question. Yeah.
Nearest object to us is our moon. What fascinates you for moon? And one more thing. I have heard of this theory that moon effects makes waves
Right.
in ocean.
Right.
So we are 70% water and we are affected by moon. Full moon, half moon.
So
moon.
the moon's gravitational force affects the Earth in that it makes tides. So what's happening there is that because gravity changes over distance, like the farther away you get from an object, the less you feel the gravity. That means that the side of the Earth that's closest to the moon feels a stronger gravitational force than the side of the moon that's farther away, or the side of the Earth that's farther away from the moon. And so that makes for sort of like a net tugging across the surface of the Earth. And what that does is that since water in oceans and whatnot is liquid, it can move around a lot easier than the Earth can, is that all of that water is sort of going around the Earth and getting tugged in opposite directions. And so then as the Earth spins on its axis, you have, you know, if you're on one location, you're going through this region of high tides and then this region of low tides and then high tides and then low tides. So there's 2 high tides a day and there's 2 low tides a day, essentially. However, the change over like the entire oceans of the Earth is like a few meters, right? The changes that you could experience in like a human body are much less. So the changes like in any movement in water in your body, which is only moving because the water is loose and fluid on the Earth, you know, it would be so small that you would not be able to detect it. And if it was an effect, you know, we would have been able to detect it with instruments that we have so far, which can measure like extremely small distances, right? So I think the only way that the moon could, you know, affect people on Earth is, you know, the moon is bright when it's a full moon, and so that could affect your sleep if you have a window open when, you know, you're trying to sleep when there's a full moon out and it's shining in your window and you're like, ah, what's that bright light? But beyond that, like, there's no real effect that the moon could have on people directly. Sorry to burst your bubble.
Breaking all the myths.
Yeah.
First of all, thank you very much for being with us at Mug Talks. It was an honor to host you. I'd like to go towards the end of the podcast with my last fascination.
Sure.
Artemis mission.
Yeah.
What's that? Where are we going?
Right. So, as we all know, the last time humans went on the moon was in the early 70s. So that was a very, very long time ago. And people haven't been to the moon since. So the Artemis missions are humans going back to the moon, essentially. And using new technology, you know, updated spacesuits, all that stuff, actually having women go on the moon as opposed to just teams and teams of guys. The mission is to bring people to the moon before the next, I think it's 2027 or 8, that will be the 3rd Artemis mission. So the Artemis 1 already happened. That was the mission which just had the spacecraft but without the people in it. It went around the moon. It was a complete success. Nothing really went wrong. Artemis 2 will be bringing astronauts farther than they've ever gone into space, to be honest, which is all the way to the other side of the moon and then back to the Earth without actually landing on the moon. And then the 3rd mission will then actually have people landing on the moon. And then I think there are plans for, like, you know, a moon base and a space station that goes around the moon and all that stuff, which will be very, very cool. What was I going to say about that? Yeah.
That's great. Again, thank you very much for being at Mug Talks. It's an honor to host you. It was an honor to host you.
Thanks for having me.
Thanks again.